We will get to the topic of bonding and anti-bonding, I promise. But first I have to answer the questions that I brought up when I was just speaking off the cuff without preparing last class about the electron degeneracy with white dwarfs and neutron stars. So first, if you have a star that dies with a mass that's under 1.4 solar masses, the 1.4 solar masses is called the Chandrasekhar limit. And that's a very carefully calculated limit, but it depends on what your assumptions are, what the answer is you get. If you use standard physics, you get 1.44 solar masses. If you use relativistic physics, you get 1.39 solar masses. So somewhere around 1.4 solar masses is the maximum mass that you can have and be held up by electron degeneracy. Now, I said electron degeneracy a few times in the last lecture and just now. What does that mean?
Yeah, I guess, well, there are multiple eigenvalues that are the same, I guess, given so by different eigenvectors you get first state.
Okay, that is the strict definition. That's the one that you've used up to now. Multiple eigenstates.
Can you, by chance, share your screen?
Oh, you know what? When you guys didn't answer, I think is when it turned it off. I had actually turned around and made sure it was up there when I called the first time, but it was the third call this time. You got it now, right?
Yeah.
Yeah, okay. So multiple eigenstates with the same eigenvalue. That's what it means. In this context, electron degeneracy means two electrons with the same set of quantum numbers. So in the same state. And we learned that for fermions, das ist verboten. And so the fact that we cannot have two electrons in the same energy state means something has to happen. Now, I say two electrons in the same energy state. Let's make sure we're clear. If I have a hydrogen atom here and a hydrogen atom here, their electrons can both be in the same energy state. It's only when they're indistinguishable. So like if I get two hydrogen atoms close enough together that they might bond, then the electrons become indistinguishable and then they have to be in different states. So when we talk about something like a white dwarf, the white dwarf has collapsed and you have, well, what are the things you're going to have in the or in a white dwarf? Okay, helium, oxygen, and carbon. Carbon's the one that's considered the most common of them, but you can have a helium white dwarf. Most of them are carbon white dwarfs, but you're going to have some others. In all of those, you have one neutron for every proton. And so you should have one neutron, one proton, one electron. So the total mass per electron is 2 times the mass of a baryon plus the unnecessary to add up mass of an electron. I was looking up why the neutron star and the electron white dwarf have different sizes, and that's part of it. The critical mass, that Chandrasekhar limit, is based on the mass per electron that you have. And so the mass per electron is 2 baryons, 1 proton, 1 neutron, in essence. Okay, so when the star collapses, the electrons get closer and closer to the point where they're indistinguishable electrons, and you can't compress them anymore and have the electrons remain in the same energy states. So they have to start piling up. Now you think about this, a free electron has any energy possible, right? Free electrons aren't quantized, but as soon as you have it bound, and in the star it's bound by gravity, then you have quantum energy levels. And so these electrons have quantum energy levels, and you have to have them start stacking up to higher and higher energy levels. And so what you have is electrons in the, n equals 2 billion energy state. And so you have these electrons that are traveling at nearly the speed of light, just flying around, because that's the only way they can exist without violating the Pauli exclusion principle. That is, without having a state that collapses to zero, which of course can't happen. And so you have all these very high energy electrons, and if you try to put in more energy, you just have to make those electrons go to a higher energy state because you can't compress it really. And so this degeneracy creates a pressure that can be calculated 3 pi squared raised to 2/3 power h bar squared over 5 times the mass of an electron. And then this here is the number of electrons per unit volume to the 5/3 power. So that's, the density of the electrons. That's the pressure that they can withstand. That is, you're going to have to compress harder than that. If you get up to a high enough pressure, well, as the mass increases, they do shrink down because the pressure gets higher that's being externally supplied, until finally you get the pressure so high that you actually have electrons that will get close enough to protons to undergo electron capture, which is the reverse of beta decay, where the electron is captured by the proton, undergoes a particle transition, because electron plus proton does not equal neutron, but it creates a neutron. So that's what happens in creating a neutron star. Now, I say that, I looked at the end states, the death states. If you have a white dwarf that exceeds that 1.4 solar mass limit, then it will crash and explode and just leave a nebula. So white dwarfs well, I'm going to write it correctly. And this can only happen when it has a partner. That word is cloud. So the white dwarfs, if they gain mass and get past that Chandrasekhar limit, then they will leave just a cloud and nothing else. So that's what happens to a white dwarf. It doesn't make a black hole ever. It will just blow up. And so if a star at its death stage is less than 1.4 solar masses, it just blows up. If it's more than 1.4 solar masses, then it will do that electron capture, create neutrons. And if it's less than, we think the number is around 3 solar masses. I was looking it up. There's very careful calculations, and those calculations say between 1.5 and 3 solar masses. Very careful with, an uncertainty of 33% or whatever. Then you would have a black hole form rather than a neutron star. So when the star dies, if it's more than 3 solar masses at death, it should make a black hole. If it's less than 3 solar masses, it should make a neutron star, unless it's less than 1.4, in which case it makes a white dwarf. And so you have black hole can be formed from the collapse of a massive star or the neutron star. The neutron star, you asked this question specifically, Indy. And so I looked it up. They have shorter de Broglie wavelengths. And because of those shorter wavelengths, you can actually pack them closer, and hence the size of a neutron star is about, was it 1,000th the size of a white dwarf? I mean, they're really tiny, even though they're much more massive. And nobody actually knows what happens if you, okay, I have it here. What happens if a neutron star collapses? No one knows. We have not observed that. The hypernova, also known as a superluminescent supernova, is not what I was thinking yesterday when I was talking about it. I have a textbook that uses that term, and I think it must use it wrong. One option is that you could create a quark star. So there is ongoing research into what that would be and how massive and dense and small and so on it would be. But it's what we know about quarks is not enough for anybody to say, yes, this is definitively what a quark star should be like. I did not find this particular statement, but it seems to me that quark star could conceivably, you go from a white dwarf to a neutron star and it's 1,000 times smaller. Well, if you go 1,000 times smaller again, you're going to be getting somewhere close to the size of the quark star being similar to the Schwarzschild radius for your mass. And of course, if the quark star is smaller than the Schwarzschild radius, you don't know there's a quark star. You just know it's a black hole. Black holes, you have so much mass that you warp the space-time around it, nothing can come out. And so there could be a quark star in there. No one would ever know. Yeah. So that's just, that is quantum mechanics stuff relevant to what we've been studying. Not in the textbook, not something I had actually intended to talk about last class period, but since I brought it up, I had to finish it out. Your lights are on. You guys look pretty dark in my picture. Do you guys see a picture of do you have a monitor with your picture?
I'm thinking it's just your side. Yeah, I think we're normal.
Okay. I can see you, but yeah, you just look darker. Okay, so getting back to where we were before we went on that little jaunt, we saw that the separation between charges is different if they're indistinguishable, if they're bosons, or if they're fermions. We're going to expand this a little more. First, when the particles are far enough apart, then they're distinguishable and we don't have the fermion-boson difference. The exchange force, the fact that one's either symmetric and one's anti-symmetric, that's what we call it, the exchange force, makes the bosons so they actually will come closer together, which would be a bonding situation if you had two electrons that are pulled closer together, or pushes them apart if they're anti-symmetric. What we did not talk about when we were talking about the symmetry, anti-symmetry, is the spin state. We saw that the Pauli exclusion principle applies if we have fermions, but the Pauli exclusion principle is going to apply if we have a total anti-symmetric wave function. If we have a total symmetric wave function that's symmetric under exchange, then we don't have the Pauli exclusion principle. So we have to include both the spatial wave function and the spin wave function to get our complete wave function. And so that's going to make a difference. Notice this statement in bold. There would be no bonding if our spatial states were always symmetric. It would make a non-existent world, right? We would have nothing sticking together. So electrons, if we have a hydrogen atom, separate them, the electron is distinguishable. If we want to try to bond them, they're going to become indistinguishable, and that's when we have to worry about this. So remember, we had the singlet state. The singlet state was actually, I should make it normalized. That was our singlet state, antisymmetric. And then we had the triplet state. And the middle one's the only one we actually care about in this context. The other two are clear. Right? There's no exchange difference in the 1,1 or the 1 minus 1, right? It's clearly symmetric. And then because of the plus sign, the 1, 0 is symmetric. So the triplet state is symmetric, and when you join it with an antisymmetric spatial function, it won't bond. The singlet state is antisymmetric, so when you join it with the symmetric, I said that wrong. When you join it with the symmetric spatial function, then you will be able to have bonding. So the singlet state can bond, the triplet state can't. And that's why you have bonding orbitals and non-bonding orbitals. If you're in this state, then you can form a bond. But if you are in this one, once again, it is verboten, forbidden. Good to know, right? Especially for Christopher, who's never taken a chemistry class and never will. That was right. You hadn't taken one, right? Chris?
Not since high school.
Yeah, not since high school. Now, for the rest of the class period, I want to review what we've learned about the hydrogen atom. What are these pictures? Yeah, I believe these are STM images. That's what I think they are. I'm not sure. But they're showing you actual measurements of where the electron density is found. I put these in the slide 4 years ago, and I had my source then, but I don't remember it now. So our method. Our momentum operator had to be made into a 3D momentum operator. Because of spherical symmetry, we used the Laplacian operator. What's the Laplacian operator? That. And then we separated variables so that we separate out the angular portions from the radial portion. Then we further separated the azimuthal from the altitude. And then we started finding solutions. And so the first one we found was the azimuthal solution, which was simple e to the I m phi. Right, that was our azimuthal solution. And then we went to the altitude solution, and that was complicated as all get out. yeah, it was. Then we went to the radial solution, and that was equally complicated. With the so here I have those steps involved. The azimuthal solution introduced one quantum number. The altitude introduced another quantum number and the requirement that m can't be greater in magnitude than L. So m could be anywhere between minus L and plus L, but that was it. And together those gave us our spherical harmonics. Then we went to the radial solution, and the radial solution, we used a similar method to what we did in the analytical harmonic oscillator solution. We first solved for the limit of large radius and found that we have to have the exponential decay. Then we solved for the limit of small radius. And then we said, now we're just going to multiply it by an infinite polynomial. Why infinite? You probably recall later on we're going to say it can't be infinite, but we started by saying it's infinite. That was why we took away the infinite, but why did we start with the infinite polynomial?
To get all the solutions, like the smaller range, right?
Well, I think Chris was in the ballpark there. If you're going to use Fourier's theory says that you have a linear combination of all of the states possible can describe any function. And so we started with Fourier's theorem and said, well, if we have an infinite polynomial, then that will, by definition, allow us to have any function. So it'll be whatever function we need. But then we said, but if we look at the boundary, in order for this to be normalizable at large radius, it's going to have to terminate, or it's going to overpower our large radius solution. And so that's, and somebody, I think it was Chris again, had already mentioned, it has to terminate so that it's not going to dominate a large radii. And so we got from that our requirement that's from the termination condition that L must be at least 1 less than n. So L can go from 0 up to 1 minus n. And then we have the whole thing put together with 4 quantum numbers. I'm definitely going to finish early because the review is not going to take much time here. Hopefully you're not all upset if I finish early. Yeah, I knew it. So N tells the total energy roughly. Now, I am going to do some stuff in Chapter 5. Well, I don't know. We have 1 week. I was planning on doing some stuff in Chapter 5 next week, but it's only 1 week. Maybe we'll just review, just go back to the beginning and do some quick. So this is what we learned. This is what we learned. This is what we learned. So you're totally ready for the final.
I'm down for that.
Yeah, it probably seems like the wiser choice. Okay.
Maybe a little bit more review from test 2.
Well, I've been hammering you guys on the commutators. I'm not going to have that mistake again.
True.
I did grade exam 3, didn't I?
Yes, I think so. Yes.
Yeah, just making sure.
I had sent you an email on it. Yes, now I remember. Because for the test score, I had emailed you about it.
Yeah. It's Friday. It's late in the day. I mean, past noon on a Friday, Seventh-day Adventist, you're not supposed to be at work. You know that, right?
True.
I mean, administrators at our church colleges certainly don't work afternoon on Fridays. That would be non-Adventist.
True. We know that.
Okay. So the quantum numbers, N, our principal quantum number, which primarily is telling us the kinetic energy. What is it really telling us? We just talked about this. What does N really tell you?
Something about the radial solution.
The number of terms in the radial solution. Okay, then we have L, our angular momentum quantum number, or azimuth. Whoa! That's not it. Emsabel is the azimuthal one. So L tells us the orbital angular momentum. it tells us what the angular momentum is. That goes back to what Bohr, Bohr had said angular momentum is quantized. Now, Bohr had said the angular momentum is equal to nh bar, where n was his only quantum number. Now we've gone to something more complicated. It's equal to h bar times square root of L times L plus 1.
Yeah.
So it's not even the same angular momentum values that the Bohr model gets you. No one ever talks about that, that the angular momenta are the wrong values in the Bohr model. We always focus on the energies are right. And as you saw in your homework problem, the most probable radius is the Bohr radius. So, he hit the nail on the head for those two, but completely missed with his actual quantum condition.
You won some, you lose some.
Yeah, that's right. M sub L is telling us about the azimuthal value. It tells us primarily its orientation of the angular momentum, because the angular momentum parallel to the external field is m sub L h bar. And then you get that really odd thing of, really? So it can't be aligned with an external magnetic field? No matter what direction I choose, it can't be aligned, and all the answer we have is yes, that's right. And what does the angular momentum vector do when you put the, let's say, electron in a magnetic field? It precesses. That is changing direction, so I took it as correct.
Yes.
It goes like this, like a top.
Right.
In fact, the top is a perfect analogy to what it's doing, because the top's angular momentum is indeed precessing because of the torque that's being applied by gravity. Here it's precessing because of the torque applied by the magnetic field. So we saw how to calculate the Larmor frequency, the frequency with which it's going to precess. So if you were to suddenly, say it's precessing like this. If you say, well, I'm just going to choose a random angle that it's going through and put my magnetic field in that direction, it seems logical to say, now I caught it so that it's parallel. But quantum physics says, no, it's just going to precess around your new axis, which is troubling. It seems like if I time it right, I should be able to hit it. Finally, M sub S tells us the orientation of the spin. Now, we should talk a little about the spin. The spin is a misnomer. The idea goes back to Wolfgang Pauli, famous for the Pauli exclusion principle, who proposed that it's spinning because of the shift when you put the electron in a magnetic field, shift in energy. And then you had the next year, I think I told you about the student, the one that wasn't my son that was shadowing. He was reading a book called, I don't know what it's called, Q or something. Anyhow, these guys here are called the spin doctors, because they're the ones who really worked out everything about spin. And of course, what were they? They were wrong, but that's okay, because they advanced our understanding. Now, here's something that still bugs me today. I'm the teacher. We talked about angular momentum, and angular momentum causes a magnetic moment. And that's something that I'm really strong with. I know that if I have current going through a coil, it's going to create a magnetic moment. So the idea of something with charge, rotating, having an angular momentum, I'm good with that, creating a magnetic moment. With the electron, we've decided that the electron doesn't physically spin. It doesn't have an intrinsic angular momentum. It has an intrinsic magnetic moment. And yet in all our calculations, like when we were adding angular momenta, we treated the spin as an angular momentum vector. And we added the angular momenta quantum values to get the total angular momentum. So I showed you that J, remember when we were doing the Clebsch-Gordon coefficients, the first time we saw the combination? J is equal to, well, I should use lowercase here. J is equal to L plus S with the rules that this is anywhere between those extremes.
Right.
The values are always positive, so there's never a negative value for the angular momentum or the spin. And so we're treating spin exactly like it's an angular momentum when it's an intrinsic magnetic moment. I'm still not sure how that is going to work out in real life, but I know that's how we do it in quantum mechanics. Now, something I've also mentioned, we have L, and that gives us M sub L, S, that gives us M sub S, J gives us an M sub J. So we haven't done anything with the J's, and we're not gonna, but that's something that you might need to know somewhere down the line. Somebody says, well, you take quantum mechanics, you understand how angular momentum works. You have J and you have M sub J, and you'd be like, no, the M sub J is talking about the orientation of the total angular momentum that's calculated by taking L plus S. And those Clebsch-Gordon coefficients, it works the same whether you're doing L's, S's, or J's. Spin. I put this actually on my physics test last week. Actually, no, it was this week, this Tuesday. You have 4 quantum numbers that you need to describe the state of the hydrogen atom. N, L, M sub L, and M sub S. I gave them 5 as an option they could choose, but no one ever says that you need the S quantum value to describe the hydrogen atom. Why not? Why don't you need the S value? S always equals 1/2. We don't need to specify the quantum value because it can't change.
Okay. For electrons. Okay.
Yeah, for electrons. Electrons, just like protons, just like neutrons, always have a spin of 1/2. And so because they always have a spin of 1/2, we start to get lazy, which confuses the issue. We say it's a spin up or spin down, or spin 1/2 or spin minus 1/2. That's not the spin. That's the orientation of the spin. That's the M sub S. And so we start to get sloppy in the language because nobody ever talks about this quantum number because it's always the same. Almost to the end of my review. I looked over at 15 minutes. We used the majority. I mean, when 2 particles are combined, the spins add just as I showed there. And if you have more than one state that will give you the same total spin, remember with 2 electrons, this had an orientation M sub S of 0, but so does this. And so because of the degeneracy there, using it in the strict sense, degenerate, then we created the 2 orthogonal states And then we determined which one was the spin is equal to 1 and which one was the spin is equal to 0 by using the raising and lowering operator on one of the other states that we know has to be L equals 1 or S equals 1. That's what's written here. And nope, not my last one. When combining, yeah, we get symmetric and antisymmetric. The triplet states are symmetric states. And when combining two electrical electrons in the triplet state, you're going to have a spatial function that would have to be antisymmetric if in the triplet state, and that's anti-bonding. In the singlet state, then it's going to be bonding. And so, whoops. Singlet state gives you bonding orbitals. The triplet state does not. Now, one of the homework problems I'm going to give you, that is the end. One of the homework problems I'm going to give you is to find the spin state for 3 electrons. And we'll start it now because we do have 14 minutes left. What would you do with 3 electrons?
Well, they would end up being indistinguishable, right?
Right. We're talking about 3 indistinguishable. Yeah, right. If they're distinguishable, then it's easy. Psi A, psi B, psi C. We're multiplying together and we're done.
Yeah.
How would you go about doing it?
Would you just use the first 3, like B equals 1, and then you have, like, the first energy state, you have, like, the L can be.
It sounds like you're working in the right direction, Andy. What was your thought process behind what you just said about, you said L, but S equals 1. What was your thought process there?
So I was thinking that, like, in the first energy state, you can have electrons in different holes, I guess you could say, in the orbitals.
Well, I'm just looking at combined electrons. I'm not in an atom per se here. Just combine the spin states. Right. What we've done is, go ahead.
Since they can't be in the same state, technically, so they have to be in different energy states, right? So they can't have the same S and M sub S numbers or something like that sort of.
Well, yes, we do have the Pauli exclusion principle if it is in an antisymmetric state. But we're going to have to find the states before we can determine if it's antisymmetric or symmetric. And that's our goal. Right, so before, let's just back up. Here, we had 3 states. I only wrote, or 4 states. We had these 2 that I didn't write. Those are all the possible combinations. How did we get those combinations? We did it directly. We just said, well, how can we combine? We can have them the same, the opposite, different orders for the opposite, and we came up with them. So we could start by doing that. It may not be the fastest way, but it might be the most obvious way to you. So we have this. These three are all degenerate, right?
Yeah.
And then the next would be these are also degenerate. So those are all the spin combinations I could get. Now, what is the S value for the top one here?
1.5.
And for the bottom one?
Same thing. 3.5.
These here could be 3/2, or they could be 1/2. So we're going to have to figure out what our combinations are to get those. So this is going to be a little more complicated. I'm going to do half the problem. So you have those four states that you get. And we can use the Clebsch-Gordon table, or we already know exactly what those states are. And then we're going to say, okay, if I combine an electron with this, so now I can combine this state with an electron, then I could have, I have S equals 1, and those combined would give me S total equals 3/2 or 1/2. And I can use my Clebsch-Gordon table for 3/2, 1/2 to find what my superposition states are for each one. And so I would find my superposition state with the 1, 1 and the final electron to get my total state for 3/2, 3/2, and 3/2, 1/2, and 3/2 minus 1/2, and 3/2 minus 3/2, and so on.
How did we get the four states?
These states here?
Yeah.
Those, we did them directly up here, right? Because this is and this is, right? So those are the states that we've already found.
Right.
And so now I'm going to use those as saying I'm adding this. And of course, you're going to find, well, that it comes out to be complicated, but you should have how many total states. You're going to have 3/2, the quadruplet state there, and the doublet state there. So you're going to have a total of 6, actually. And use your Clebsch-Gordon tables to do all the work rather than doing it directly. Remember the Clebsch-Gordon table? That's the reason I'm giving this problem to you, to give you lots of practice with it. All right. We'll end 4.5 minutes early. All right. Have a happy Sabbath. I'll see you next week.
Yeah. Thank you, Jim.
All right.